Good morning, everyone. See you again. And this is our second class. And from today, and we will like dive into the real physical knowledge. And today we will talk about oscillations and what is that, and how to explain it, how to understand the theory behind that, and how to calculate how to represent the oscillation with mathematical equations and how to calculate the force and when the oscillations happened. Yeah, so today we will talk about all these things. And I don't know if you guys finished the reading assignments and quizzes, and you better to finish that before you watch this video. If you haven't, please stop this video and finish the reading assignment and quizzes, and that will be better. Finish that and then watch this video, and I think that will make the this study more efficient. Yeah. Okay. Let's start today's class, and let me share my screen and talk about what we will learn today. Share. Uh, let's start today's class. Today we will talk about oscillations. And before I talk about oscillations, do you guys have any ideas what is oscillations? And I think now most people, like every people, see the oscillations maybe every day in the real world. Maybe you don't know what is oscillations, but if I tell you, you will know. Oh, you see the oscillations maybe every day, and then yeah, most time you can see this situation, this phenomenon. Yeah, let's see that. Mm, yeah, the chapter 40, we will learn the oscillations, and this is the goal for the chapter 40. We will understand systems that oscillate with simple harmonic motion. Yeah, oscillate, it is some repeat things, but here in this chapter, we mainly focus on the simple harmonic motion. Actually, the simple harmonic motion has some rules, and we will learn that. And there are some examples of simple harmonic motions and the winds. And if you I think everyone will have the now will have had the wind play the winds and jumper. Yeah, jumper also a kind of simple harmonic motion, and also the clock and uh, like the mechanical clock, not like the electrical clock, because the electrical clock it only shows the digital number. Yeah, this is a mechanical clock will has a simple harmonic motion. You can see it is repeat. Yeah, this repeat moves we call it simple harmonic motion. And also the metronome. And the metronome, you can see it, if you run it, it will uh, move, repeat from left to right, repeat and repeat again. And actually, there are many examples, you can think about that. You can find many examples, not only those three. Yeah, this is just the typical examples of simple harmonic. And we will actually, yeah, those kind of simple harmonics, we will have a specific rule to describe that. Yeah, and in chapter 40, we will learn that. And also yeah, and before we learn the chapter 40, I want to preview what we will learn in this chapter. Firstly, we will learn what is motion, the motion that repeats. Like I just mentioned before, you can see the simple harmonic motion, the swing, the mechanical clock, and the metronome, and it just repeat from the highest to the lowest, it is repeat again and again. So in this chapter, we will learn the motion that repeats. You can see this girl moves down and the springy ropes pull up. This restoring force produces an oscillation, like one bounce after another. Yeah, like a like a, uh, this girl jump with this jumper, and it will up down up down up down, and it is just like the a kind of oscillation. Yeah, so the chapter 40 is like a oscillation. I, actually, which means the motion that repeats. Yeah, we will learn that. And uh, yeah, then we will learn simple harmonic motion. What is a simple harmonic motion? And what is what is a simple harmonic motion? And you can see, uh, I think most people most of you have went to the science museum before, and most science museum have this pendulum. And you can see if you feel the sound in this pendulum, it will give you a sinusoidal figure, and the sound records the motion of the oscillation pendulum. The sinusoidal shape tells us that this is a simple harmonic motion, which means all the simple harmonic motion, like the move shape, and you can be represented by a sinusoidal shape. Yeah, and all oscillations show a similar form. Like I said, all the simple harmonic motion will just like a sine function, a sinusoidal function, a sinusoidal shape. Yeah, and you can see if you do this lab in a science museum, and you can see there will be a sinusoidal shape, uh, like. Figure. But I don't know if you notice when you do this lab in like science museum, and the sinusoidal shape will at the beginning it is the amplitude is big, but slowly it will stop. Yeah, actually this called like a damping situation. We will talk about this next tomorrow, and which means there are some friction, this friction from air environment, and and this friction will make this pendulum stop. But when we try to learn how to describe and analyze oscillation system, we suppose it is an ideal system, which means there is no friction. Yeah, because when you do a lab in a real world, yeah, there are so many factors will affect the move of this pendulum. Yeah, so when we describe and analyze oscillation systems, most time we will suppose this is ideally like a oscillation system. Yeah, and we will talk about this today in today's class. And also, this is we will talk about tomorrow, resonance. When you make a system oscillate at its natural frequency, you can get a large amplitude. We call this resonance. Yeah, sometimes I don't know if you have this experience, like a like a sometimes when a thing moves at a specific frequency, if you if you maybe do something or make some sound with in a same frequency, and you can get a large sound. For example, I don't know if you have this experience. Some people maybe use the pen, draw something on a blackboard, like a real blackboard. There will be some sharp noise. Yeah, you can your air can hear. Yeah, this kind of like a phenomenon we call it resonance. Yeah, you can see like in our like air we have a membrane, and this membrane will like move in a specific frequency. Like if like there is another sound has the same frequency, like it will make a resonance and we can hear a very high pitch of signal of sound. Yeah, and we will talk about tomorrow. Yeah, don't and all the details. I will no, I will give you. So don't worry about this one. Okay. Okay, this is today's goal. And firstly, we will review the concepts of equilibrium and oscillation. Yeah, what is equilibrium and what is oscillation? And after that, we will learn the definition and the characteristics of simple harmonic motion. The short name is SHM, and in today's class, and I will use SHM to stand simple harmonics motion many times. So don't be confused if I use the SHM. Okay, and like after that, after we know what is a simple harmonic and what is a characteristics of SHM, and we will learn how to describe simple harmonic motion. And after that, we will explore the relationship between SHM and uniform circular motion. Actually, the most important part in today's class is this part, learn how to describe simple harmonic motion. Yeah, you can see all this part, these things, and these things actually is just a prepare to prepare like let us understand well like how to describe as HM. And the next one is just some like application, some like extended knowledge. Yeah, this is today's goal. Let's begin. And okay, let's talk about what is equilibrium. Uh, I think these ideas you have already heard about this. Like the equilibrium position is just like a standard still position. When you put a ball, when you put like a ball in a ball, like when you put a ball in a ball, and if you didn't give this ball a force, and it will like stay here stillly. But if you put a ball like from this location, like, and it will like because of the gravity force, and it will like run like this and back and back and up and down and up down and up and down and until like it will stop here like after a long time. Yeah, this point we call it equilibrium position. Yeah, and uh, so yeah, like this marble that is free to roll inside a spherical ball has an equilibrium position at the bottom of the ball where it will rest with no net force on it. Yeah, which means yeah, if this ball in this location, you can see this one. Yeah, this one is the support force from the ball, and this is the gravity force, and those two force and can generate a net force. This net force will make the ball run from here to here, and then the opposite like force, which means yeah, this is the support force, and this is gravity, and there will be another net force, which this net force will make the ball down. So like in this like position, equilibrium position, which means there is no net force on this one, only the gravity force and the support force. Yeah, and if pushed away from equilibrium, the marble's weight leads to a net force towards the equilibrium position. The force is called restoring force. Yeah, we call this force the restoring force. So this I just this slides just tell you what is equilibrium, and firstly we learn what is equilibrium, what is oscillation, and then it will help us to understand what is simple harmonic motion. Okay, this is equilibrium position and equilibrium status and equilibrium situation. Yeah, this is what is equilibrium stands for. Yeah, and if you have any question about equilibrium, please let me know. I think this one is this term is easy to understand, which means some still station statues. Yeah, and let's talk about what is oscillation. Okay, you can see when the marble is released from the set, it does not stop at the bottom of the ball. It rolls up, yeah, it rolls up and down each side of the ball, moving through the equilibrium position. Yeah, like I said, because there will be a force, and this force, net force, if it runs this and this marble, because it has a velocity here, so this velocity make result from this net force, and then this velocity makes a marble goes up. Yeah, and oh sorry, oh sorry, let me know what it is. Okay, this repetitive motion is called oscillation. Yeah, the oscillation. I think you can think it is just a repeat motion. Yeah, and the oscillation is just like the repetitive motion, like the motion repeat again and again and again and again. We call this kind of situation oscillation. Yeah, and this is two very important term. One is equilibrium, and the other is oscillation. Equilibrium, which stands for still status like that, and the oscillation, which means it talk about one situation, like it moves, repeat and repeat. Yeah, and any oscillation is characterized by a period and a frequency. You can see if we put this marble here, and it will down, up, up, down, up, down. And yeah, when we talk about this oscillation, we suppose there is no friction here. Usually in the real world, because there will be a friction, and the ball will stop here. But when we describe this situation, analyze this situation, usually we will ignore the friction from here. So then the marble will if you put the marble here, it will up or down, up, then opposite, and it will repeat continuously. And this continuous situation, we can represent this motion by a period and the frequency. Actually, we will talk about frequency and period. I think this period, frequency and period, you guys have already learned these two term in some classes, am I right? Because this is very basic things. You can see there is an example like a electrocardiogram. We call it ECG. Like a it's complex, but it has a repeat pattern. This is just like a beats of a heart. You can see this like a beats of heart. It produces approximately the same signal. You can see there is some signal, and then there will be a sharp like a thing, and then another one, another like a short one, and another sharp one, and another short. You can see it approximately the same signal. Yeah, so one like a repeat signal, like because you can see we calculate from here and to here is just a one, and after that it will repeat this pattern. So just a one like a single like a beat, we call it a period. Yeah. So I think this period frequency is a very common like term to describe one signal. Yeah. Uh, yeah, and you must like heard those two terms in some like classes. If not, that's fine. That's fine. And I will tell you like the period is just like one like a single signal, and you can see from here to here there is no repeat. But after this, it will repeat approximately. Yeah, in the real world, like there are some signals, and it's now perfect. Yeah, it's now ideally. So we just approximately we just give some supports, yeah, to finish this. So, like for an oscillation, the time to complete one full cycle is called the period of the oscillation. The number of cycles per second is called the frequency of the oscillation. Actually, the period and the frequency has this. Oh, sorry. I think I just missed the. Let me see. Oh, sorry. Okay, I just missed the equal single. Yeah, actually the frequency and the period has this relationship. The frequency equal one divide the period. Like yeah, the same thing. The period will equal one divide frequency, because you can see the number of cycle per second is called the frequency of the oscillation, which means what is my frequency? Which 1 second, like I include how many different period. Am I right? Does it make sense? So like from this formula, you can get this formula. Am I right? Like T equal 1 divide F. So this is the relationship between frequency and period. The units of frequency are hertz. Yeah. Oh, I think. Sorry. Yeah. Yeah, this is units of frequency, and those two different terms is different period terms is very important to represent the signals. Okay, usually there are some like common units of frequency, like 1 kHz. Yeah, which means the period is 1 milliseconds, and 1 megahertz, and 1 gigahertz, and the period is just the opposite period. Yeah, and those three are some like common units of frequency. Yeah, you will like use those like frequency like in many like courses, and in many like area like a research area. Yeah, and okay, let's try to like practice the find the relationship between frequency and period by some questions. Okay, let's see these questions. There is a mass oscillates on a horizontal spring with period t equal 2 seconds. What is the frequency? Okay, do you know that? And if you met this problem, just remember the relationship between period and frequency. What is frequency? Frequency equal 1 divided t. Yeah, am I right? Because which means 1 second I include how many period, am I right? So the period here is 2, 1, so it is 0.5, which means the right answer is A. Yeah, does it make sense to you? Okay. Any questions about this problem about these questions? Just let me know. And let us check the other questions, frequency and period question. Two, like a mass oscillation on horizontal spring with period t, also like 2.0 seconds. If the mass is pulled to the right and then released, it pulled to the right and then released, how long will it take for the mass to reach the leftmost point of its motion? Yeah. Like, so how long will it take for the mass to reach the leftmost point? Which means it pulled to right. This is the like right this is the right point. And then the question asks you how long will it take for the mass to reach the leftmost point? Yeah, which means if you pull the like mass here and release it, and it will move like this. It will move like this, and then here, and this is left, and then it will, and then back to the yeah. All the questions we suppose there is no friction. Yeah, so it will like bounce right and left continuously. So which means if the period is 2, and which means one round is 2, am I right? Yeah, the period is just like the single, like now repeated motion, which means it is just this is 2. So how long it would, I think it is obvious, am I right? So it is 1. Does it make sense to you? Yeah, because let me try to, is there some eraser? Oh, sorry. Keep. Okay. Let me try to make it more clear for you. Okay. Yeah, because, for example, this is the equilibrium position, for example, EP. And I pull this like a block here and release it, which means it will move from here to here, and then to the left one, and then to the get the left one, it will back, and then to the original point. This is a 1 period. Does it make sense to you? Yeah, this is because you can see in this period there is no repeat thing. Yeah, and which means this process, and it will take 2 seconds. And then how long it will take for the mass to reach the leftover, which means it is just need 1 seconds. Does it make sense to you? Yeah, this, if, yeah, any questions, just let me know. Okay, let's see the other question. A typical earthquake produces vertical oscillation of the earth. Suppose a particular quick oscillation the ground at a frequency of 0.50 Hertz. As the earth moves up and down, what time elapses between the highest point of the motion and the lowest point? Yeah, it's the same thing. Between the highest and the lowest, from highest to the lowest, it is half period. Am I right? Yeah, because 1 period is just like from the high to low, low to high. Yeah, this is 1 period. Remember, 1 period is just like include no repeat thing. You can see from here, this direction is here, this direction is here. And the other their period is just repeat this pattern. So which means this is just 1 period. And it just asks you between the highest point to the lowest point, which means just half of the half period HP. And we now we know the frequency. And firstly, we need to calculate the period, am I right? So what is the period? We know the period is what? 1 divided f, am I right? So it is 1 divided, and then you just half period, so it just divide 2 again, am I right? So which means it is 3.3 seconds. Yeah, you can calculate it. Yeah, and any question about this one? Okay, if you have any question, just let me know. Okay, this is like the basic thing before we talk about simple harmonic motions, SHR. Yeah, for now, I want to summarize. Like we talk about what is equilibrium. Yeah, equilibrium is just that status, it is still, like keep still there. What is oscillation? Oscillation just repeats. And what is frequency and period? Actually, frequency and period is just a describe oscillation. Yeah, because the oscillation as a repeat, and one repeat, one like a non-repeat motion, the time is a period, and the period and the frequency has some like a relationship. Yeah, you can after you know that, and it will be easier for you. And after we talk about this basic terms, and let's talk about what is simple harmonic motion. Yeah, you can see, like we talk about this like a marble. The graphing of oscillation motion has a form of a cosine function. Yeah, you can see if we put a ball here, and then the position is, for example, just for example, and the position here, maybe it is 10, for example, and then it will like go down from here because this is equilibrium position. It is just a 0. We call it 0, and then it will goes to this position. This position you can it's totally opposite with this one. Am I right? So we call it maybe like a negative 10. This is positive 10, and then it will be back to the 0 here, and then it will go to the original point 10. Yeah, and because like remember we just suppose this is ideally like a motion. There is no friction, so it will like repeat this motion again and again. So you can see if you like connect this point, it's just a cosine function. Does it make sense to you? Yeah, a graphic and a function that has a form of sine or cosine function is called sinusoidal. And a sinusoidal oscillation is called a simple harmonic motion. Like yeah, if this like a oscillation has like a sinusoidal form, yeah, we call this a simple harmonic motion. Actually, there are many like things. There are many examples. We can like use simple harmonic motion to represent it. Yeah, you will see that. So now, do you know what is simple harmonic motion? Just remember, if you can represent a motion using sinusoidal like a function, you can see, and this oscillation, we call it simple harmonic motion. Okay, let's continue. Yeah, most cases of simple harmonic motion can be modeled as one of two simple systems: a mass on a spring and a pendulum. And you can see here, like most cases as like a simple SHM can be modeled as like otherwise or like a mass or like a pendulum. Yeah, you can see it just like similar like this like a vibulate, like oscillate. It's just otherwise it's just like this from left to right. Otherwise it is from up like a big like to the low the equilibrium, and then down up and down. Yeah, this kind of motion, or otherwise from left to the equilibrium to the from right to the equilibrium to the right left, and like repeat again. Yeah, this is most cases of SHM can be modeled as like one of those two simple systems. Yeah, there are two like related real world examples. And vibrations in the air. Like I said, the sound waves entering the air cause the oscillation of a membrane in the cochlea and part of the inner air. The vibration can be modeled as a mass on a spring, which means you can see in your like air, there are some like yeah, I will talk about it later. Yeah, detailed. Yeah, in your air, there are some like some structure, and those structures similar like a spring. It moves from left to right, left to right, left to right, and uh, the sound will cause vibration, and just like a spring. The period of oscillation of a segment of a membrane depends on mass, the thickness of the membrane, and the stiffness, the rigidity of the membrane. Actually, yeah, you can see. We will talk about this spring more details later. And yeah, there is another like example, the motion of legs while walking. Yeah, the motion of a walking animal's leg can be modeled as a pendulum motion. You can see it was up, down, up, down, up, down, up, down. Yeah. And the rate at which the leg swing depends on the length of the legs and the free fall acceleration G, like gravity G. Yeah. Uh, okay, this is two like very typical examples. Yeah, and let's continue talk about it. And actually, we know what is like a simple harmonic motion. What is it? Let me recall it. Yeah, I just talk about it. Yeah, if you can represent like a move with in a like a sinusoidal form, we can call it a simple harmonic motion. Yeah, just remember it. Yeah, and if we displace a glider attached to a spring from its equilibrium position, that the springs exerts a restoring force back toward equilibrium. The net force on the glide is simply the spring force. Yeah, you can see if you like there is a in the at the equilibrium there is no net force, but if you pull it to the like right, there will be a displace causes the spring to exert a force towards the equilibrium position. Actually, this force equal K is spring constant. The specific spring will have the specific constant, so don't worry about the K. The X is just the displacement. Yeah. So the negative sign here tells us that this is a restoring force because the force is in the direction opposite the displacement. If we pull, you can see if you pull the glider to the right and the x is positive, but the force is like make pull the glider to the left. So the force is to the left, backward equilibrium. Yeah, so that is why here is a negative sign. So like this is for spring for like spring with mass, and we can like represent the like display the spring force using these equations. And I don't know if you have already learned this like equations before, but I think you may have already learned this in high school physics, if I don't remember wrong. Yeah, but that's fine. Yeah, the spring force equals the negative and the spring constant and the displacement. Okay. Let's talk about more molecules. Let's try to stop video manage. Okay, let's continue talk about SHR. And I think like you guys already noticed there is another like term linear restoring forces. So after I talk about these equations, do you know why the linear restoring forces has a relationship with SHM? So do you know what is a linear thing, linear relationship, linear forces? Linear means there is no like it's just like the one like a variable increase with a specific rule like like as the other variable changes, which for example this x change like decrease like increase, and this net force increase just with a specific rule, like this rule is a linear. If you draw a figure for this one, it's just like this. So which means this variable and this variable, it has a linear relationship. So we know there is a so we can know this is a linear restoring force. The net force is towards like a equilibrium position and is proportional to the distance from equilibrium. Yeah, you can see this net force and this displacement has a linear relationship. Yeah, so we know this is a force. We call it linear restoring force. Okay, and uh, okay, we have already let's talk about the horizontal motion of a mass on a spring. You can see the point on the like on the point on the object that is mirrored, and if you pull this grid here, and it will oscillation from here to there, and you can see this is this is you just pull it from here, and this is uh, right point and then you release it, and it will just this is equilibrium position, and it will back to the equilibrium position, and x is the displacement from the position, and it will go to the left point, and then equilibrium position, and then the right point, and repeat. The maximum distance to the left and to the right is a, which means this is a. We call it like the maximum distance. In a sinusoidal figure, we call it amplitude. So this is like the horizontal motion of a mass on a spring. You can see this is a sinusoidal shape. Okay, let's continue talk about the vertical motion. Yeah, this is a horizontal motion. And actually, the vertical motion of a mass on a spring, it is similar. For hanging weight, the equilibrium position of block is where it hangs motionless. The spring is stretched by L. Yeah, this is sorry, I think I just missed. Yeah, if you put a block here and the spring is stretched by like delta L. Yeah, this is delta L. The block hanging at rest has strength spring by delta L. This is block's equilibrium position, the point with no net force, which means in this point there is no like a net force. And yeah, you can see if you put this glider here, and it will like stretch naturally. And for stretched spring, this is equilibrium proposition. Because yeah, does it make sense to you? Okay, let's continue to talk about vertical mass on a spring. You can see like this picture at like we just mentioned. Uh, if you, this is unstretched spring, if you put a block under this spring, and then like this spring uh, will be naturally stretched and get to a equilibrium position like this, and then this spring will keep still, and in so the like force, the net force will be zero because the spring like force and the gravity force is equal. And yeah, and for the value of delta L, like after you put the block under the spring, and there will be a stretch, and this stretch length delta L is determined by solving the static equilibrium problem. Actually, like we usually use the Hooke's law. Like actually, the Hooke's law. I think you have already learned this in college physics one. You need to remember that. I know some students may not have the college physics one. That doesn't matter. That's fine. Like the Hooke's way, Hooke's law, like uh, just give us one equation, like for a spring, if the spring force equal like if the spring like stretch or like uh, stretch or like be push up, and the spring force equal like k is like a spring constant, like for a specific like a spring, the k value is fixed, and the delta L is just the like a displacement length. And yeah, for example here, and the delta L is just like after like this spring stretched, and this is the length. So the Hooke's law is very easy, and you can use the Hooke's law to represent this situation. And also the Newton's first law for the block in equilibrium is like the net force equal the spring force plus like the gravity force. And for the spring force, and it equal k omega L. Yeah, we have already talked about it. And for the gravity, like force, we know it is equal mg, and like quality and multiple the gravity acceleration. Yeah, this one is a fixed thing. And if you know the blocks quantity, that you can like you can actually you can use this equation to get the delta L, because the block, the quantity of the block is fixed. The gravity acceleration is fixed. The spring constant is fixed. So you can calculate the stretch length using these equations. Yep. Actually, these equations, from this equation, yeah, you can see k delta L minus mg equals 0, and then k delta L equal mg, and then we can get delta L equal mg divide k. Yeah, does it make sense to you? Yeah. Yeah, this is how we can get the springs stretch length. Actually, yeah, we will have a lab for the motion simple harmonics motion, and which will let you to calculate the spring constant. Actually, like the stretch length after you put the block, you can like measure it with a ruler and the mg, and you can easy to yeah, and the lab will give you the specific value, and then you can use these equations to calculate the spring constant. Okay, let's go on this part. When the block is above the equilibrium position, the spring is still stretched by an amount delta L minus y. Here, this is the equilibrium position, and if we push it up a little bit, and then the stretch will become delta L minus 1 because you pull it up. You push it up, yeah, which means the stretch will be shorter, and the net the what's this 132? Okay, I don't think there will be this one. Sorry. Uh, what's this? Uh, okay, yeah. Wait me for a moment. I think I just will write this equation. Mm, I just oh, okay. I think there is no this two, and this is K. Okay. See. Mm, and then also, yeah, I think I just put yeah. This is uh yeah, and then yeah, there is no 3, 2. Okay, yeah, that makes sense for you now. Okay, you can see in this situation, the net force equal what? Equal this force and plus this force. Okay, this force equal what? Yeah, we know this equation. For this situation, the length equal delta L minus y. So we need to replace y with delta L minus 1. And then the gravity force equal mg. And so this is because this is opposite. So there is this is a negative minus. Okay, and then I just put a key into this parallels, and then this equation can be read as k delta L minus mg minus kl. Yeah, and as we saw before, the k delta L minus mg equals 0. Yeah, here k delta L minus mg equal. Sorry about that. So based on this equation, and then we can replace this part 0. So the net force equal minus ky. This ky is just like the displacement, uh, after the block the equilibrium position and the change length like that. Yeah, so this is for mass on a spring, vertical mass on a spring, the net force. Yeah, you can use this equation to get the net force. Okay, and the rule of gravity is to determine where the equilibrium position is, but it doesn't affect the restoring force for displacement from the equilibrium position because it has a linear restorative force. A mass on a vertical spring also oscillates with simple harmonic motion. You can see like here, in this situation, and the net force only related to the spring constant and the displacement length. Am I right? It it doesn't matter like what is block weight. Yeah, am I right? So which means like the force, the restoring force, like is not related to the uh, the gravity, the mass quantity, the gravity thing. Yeah, yeah, there is a linear restoring force, like a mass on a vertical spring oscillation with a simply harmonic motion. Okay, and yeah, after talk about the spring, let's talk about the pendulum. Pendulum, yeah. Uh, Let me try to make sure. Uh, and make pendulum. Yeah, actually, a pendulum is a mass suspended from a pivot point by a lead string or rod. The mass moves along a circular arc. The net force is tangential component of the weight. Actually, you can see that if you observe the difference between the spring and the pendulum, the spring is like there is no angle change. It's just like if the vertical like a mass on a spring, and then it will like up down up down up down, and if it is horizontal, and it will left right left right left right, there is no angle like change, only like the velocity change, displacement change. But for the pendulum, you can see you like there is like a angle change. Yeah. So uh, like this angle, like you can see here, we just analyze the net force. The net force equal this thing. Yeah, this is the net force, and this is like a tense, the strain tense, strain tense force like that, and this is gravity, like the ball, this ball's gravity. Uh, and you can see this force can be divided into this force and this force. Actually, these two forces are equal with each other. And then this force is just the net force. And this net force like will change as the time pass. Yeah, you can see. And then if you observe it, and this because this is mg, this is mg, and this is the like a theta angle, which means this part is just like the mg uh yeah, this is the like a 19 degree, which means this is mg multiple sin theta. Does it make sense to you? Let me try to make it clear. Keep and yeah, you can see here. This force is mg. Sorry, is mg, and actually you can see this force can be divided into this force and this force, and you can put this force here, which means yeah, this force equal W cosine theta. This W cosine theta equals the lattice force. And then here, this force, the same force equal W sin theta. W is just a negative mg, like we negative because it's an opposite like direction. So which means this net force equal negative mg sin theta. Okay, any questions, just let me know. Let's continue. Okay, so like the equation is simplified for small angles because sin theta at approximately equal theta. Yeah, when this theta is very small, which means this s is is very small. Like this sin, the theta will like sin theta. Yeah, you can see it here, which will be this. Suppose this theta is very small, and sin theta equal what? S divide this line. Actually, we set it x, and when the theta is very small, the s equal very small. So those two all are all very small. So we can like consider they are same. Does it make sense to you? Yeah. Okay, this is called the small angle approximation. Therefore, the restoring force is like a net force. We have already get it is equal to this one, and then we just use small angle approximation, then equal this approximately equal this one, and this theta, this like a theta. Like I said, this sin theta. Why there is so many? Okay, just ignore this 2, 3. I don't know what's this. Okay, and this theta, which like I said, it is S divide L. Yeah, it is just an approximate because if this theta is very small and that L and this length will be very close, so it will be S divided L. So we can use S divided L to represent theta. And then we just put a L here and put S here, and we can get this one. The net force equal negative mg divided L, like a multiple S. What is S? S is just this move, and mg is just the gravity force for this ball, for this object, and the L is the the string length. Yeah, and then use these equations. Actually, we can calculate the string length. Yeah, and the mm, yeah, let me continue. Oh, sorry. The force on a pendulum is a linear restoration force for small angle. You can see it also very small. It also like is a linear relationship. You can see the S is changed. Am I right? The L is the string length. It will not change like anytime. Am I right? Yeah, and the mg, yeah, it's now changed, and the like the L, yeah, like I said, it's now changed. This part is a fixed. It's just like a constant coefficient like that, and the change thing is S. So the net force and the S has a linear relationship. So the force on pendulum is a linear restoring force for small angles. So the pendulum will undergo simple harmonic motion. Yeah, you can see if the net force and the like and the move length has a relationship, and and this like oscillation will undergo like simple harmonic motion. Okay, let's try to, yeah, we have already like talk about the spring, the mass on a spring, the horizontal like mass on a spring, the vertical mass on a spring, and then pendulum, and it's actually it's a similar, yeah, it's similar, not same but similar things. Yeah, and let's try to like describe a simple harmonic motion. You can see let use this like a vertical mass on a spring as an example. Yeah, the mass starts at its maximum position displaced here. Yeah, this is the maximum position displaced y equal a. The velocity here is 0. Yeah, because you haven't released it. But the acceleration is negative because there is, you can see the is here. Yeah, this is positive as we have already analyzed before. And then this, it will run like down, so it will be negative because there is a net downward force. Okay, The mass now moving downward, so the velocity is negative. As the mass near, like uh, as the mass near the equilibrium, the restoring force and thus the magnitude of the acceleration decrease. Yeah, you can see when in this point and there is a maximum positive displace, but the velocity is zero. And the like the acceleration is the maximum, and as it reaches to the equilibrium position, and the velocity will increase like bigger is a maximum, but the acceleration and the restoring force like a decrease, it will become small. Yeah, and at this time the mass is moving down with its max, like at the equilibrium position, like the mass is moving downward with its maximum speed. Yeah, it is at the equilibrium position, so the net force and thus the acceleration is zero. Yeah, you can see here the it it is the like a net force is zero, because here in the equilibrium position we know we have already analyzed it. The net force is zero, which means the acceleration is zero, but there has the maximum speed. It will rush in downward continuously. Yeah, and then the velocity is still negative, but its magnitude is decreasing. So the acceleration is positive. You can see from here to here. And the velocity is still negative because, yeah, the direction is here. But its magnitude is decreasing, it's continue decreasing. So the acceleration is positive. The mass has reached the lowest point of its motion, a turning point. The spring is at its maximum extension. Yeah, this is a turning point, the lowest point of its motion. And there is a net forward force. Yeah, and the net force will forward, it will like upward force, and the acceleration is positive because acceleration and the net force will change the direction and goes up. Yeah, and the mass has begun moving upward. The velocity and acceleration are positive because the direction is just like that. In this process, it is negative. In this process, it's positive, like that. And if you, yeah, and then we get here, and the mass is passing through the equilibrium, yeah, here, equilibrium position again in the opposite direction, so it has a positive velocity. There is no net force, so here the acceleration is zero, but the speed is maximum. And then the mass continues moving upward. The velocity is positive, but its magnitude is decreasing. Yeah, you can see the magnitude will decrease to the magnitude is decreasing, so the acceleration is negative. The mass now back at its starting position. This is another turning point. The mass is at rest, but will soon begin moving downward, and the cycle will repeat. Like we assume there is no friction, so the this spring will like bounce up down continuously. There will be no like a damp situation. Yeah, we will talk about this situation later. Yeah, this is like a simple harmonic motion, like a process, and you can see here. Uh, so all the 2, 3 is just the parallel. Okay, the positive varies time graphic for oscillation motion is a cosine curve. You can see here. Here is we draw the like position varies time graphic, as a time person, and the position from the maximum to zero, from zero to the negative maximum, and then to the zero and to the maximum. This is one period, and yeah, it's just like a cosine curve. So we just write it like this, and xt is equal a. This is the maximum displacement, and cosine 2 pi t over t. Like this is just as a this cosine function, and 2 pi 2 pi t is just like a it's just as a like a standard like a circle function. You can, if you want to represent this function, you can use this if you want to represent this figure, you need to use this function. I think you need to review, if you want to know why, then you need to review the mathematical theory. I think this is very basic circular functions, and xt indicates that the position is a function of time. The cosine function can be written in terms of frequency. Sorry, this is also yeah, and you can see we can. Do you still remember the relationship between period and frequency? Try to remember a little. Yeah, it is f equal 1 over t, which means t equal 1 over f. Then you can see here is 1 over t. We can like replace f. We can replace t with f. Yeah, and then we can get this equation. Does it make sense to you? Okay, let's continue. And sorry, why is it just like this? It's weird. I think the iPad makes the slides it's weird. Format is weird. So yeah, we just need to uh, put it here. Okay, like the velocity graphic is an upside down sine function with the same period t. You can see this is like a velocity from the starting point. The velocity is zero, and it because it goes down, so it is negative. It will reach to the biggest, the maximum to when it gets to the equilibrium position, and then like after, and it will like continue, it will like the velocity will decrease, and until it reaches the like uh this is the uh like the lowest position, and the velocity will be zero. It is like the and then the direction will change to positive, and it will like increase when it gets to the other equilibrium position, and then decrease. Yeah, this is a velocity. If you observe it, and you will find that it is a sine function. Do you know the difference between this cosine function and the sine function? Why this is a cosine function? Because when it is zero, it is equal a, which means yeah, when it is like t is zero, cosine zero equal 1, so it is a. So and why this is sine function? Because sine function, when the t equals zero, which means sine, like sine function equals zero, so which means like the velocity is zero. Why there is a negative? Because at the beginning it is negative and then positive. Yeah, so we can here the maximum velocity, we call it v maximum, and then multiple sine function, and there is a negative symbol because it goes down then goes up. Yeah, and the restoring force causes acceleration. This acceleration we can represent like use net force divide the quality, This is, I think this is also you learn in the college physics one or the high school. Yeah, the acceleration equal like the net force divide the quality of these blocks. And we know the net force equal negative kx. Yeah, we have already learned that, we have already analyzed that. Let me show you. Yeah, as for the pendulum, as this is just the length, and for the mass on spring, this is just like the y is just the displace. Yeah. Okay, let's continue. So, which means the like ax like the acceleration various time graphic is inverted from the positive versus time graphic, and can also be written. You can see this one and this one is just the opposite. Am I right? Which means it is like this is x a cosine 2 pi f t, like a cosine 2 pi t divided t, which means it is equal like a negative a maximum cosine 2 pi t over t. Yeah, it's just like use just opposite give a negative a maximum. Yeah. And then we use the frequency to replace the period. This one is obvious. Then like we can get the equation for the acceleration. Okay, actually, yeah, we know like for now we know the like for a simple harmonic motion, the the position will be a sinusoidal function based on the time. You can see based on the time, it is a sinusoidal. And also the velocity is also like a sinusoidal function based on the time. And same thing with the acceleration. So which means like the for the oscillation, for the simple harmonics, they have the sinusoidal relationship. A quantity that is oscillates in time and can be written x equal this one or this one. Yeah, because you can see sometimes you just you just put stretch like a pull up, pull down the spring. Sometimes you just pull up the spring. For example, your like initial point is from here, and then it will be just like this. Or sometimes your like start point is here, and it will be just like a a sine function like that. Yeah. So which means the sine cosine it doesn't matter because it's just like the 20 but just a 90-degree difference. Yeah, and we call this is called a sinusoidal function with period t. The argument of this function the argument of this function 2 pi t over t is in radians, which means have you ever heard about radians? Like you can see like 2 pi is just like a circle, like a zero, like a pi divided 2 and pi and 2, 3 pi, and then it's 2 pi. Like it's just a circle. And then you just like the t is from 0 to t, and uh, t divided t is just like from here 0, for example, t from 0 to t. 0 to t, it is just a one period, and then it will like from like 0 to 2 pi. As if the t like over like if the small t over the period, and it will go on the next period. So which means it will circle like this, and the sine function same value is just from 0 to a to 0 to negative a, blah, blah. It's just like this is called the radians. The graphene of both functions have the same shape, but they have different initial values at t equals 0. Like I said, if the sin cosine is just like your initial position is different. If your initial position is here, it is cosine. But if your initial position is here, it is just a sine function like that. Yeah. So okay. And actually, there are some limits. Yeah, if x is a sinusoidal function, then x is what? Yeah, there are some, it's bounded. It can take only value between a and negative a. Yeah, because it will not like over a or over negative a, because the same function is from like 0 to 1, 1 to 0, and 0 to negative 1, to 0, like that. And so the bounded it is like limited. It only the value x is only from between a to the negative a, and it is periodic. It repeats the same sequence of values over and over again. It is a period. Oh, I cannot say it is limits. It's just some features, characteristics. Whatever value x has at time t, it has the same value at t plus the period. Why? Why is that? Because it's period, which means the t plus uh, the like variable t plus the period t, the same. It's the same thing. Like I just talked about, it is a circle. After one circle, yeah, from 0 to t, and it's just like take the all 2 pi and over, if the t over t, and it is just like the same thing to it's just a circle thing. And the special value, the function x has some special value at certain times. For example, when this is the function for like x, and when t equals 0, and for the sin it is 0, for the cosine it is a. When t equal quarter t, and it is x equal a like the maximum displace, and the cosine will be 0. Yeah, so you need to I think you don't need to memorize this, but this is very simple, like a sinus like sinusoidal function features, and yeah, you can easily to get it. Yeah, like when t equal half period. Yeah, half period, which means 2t, and then it is half pair. Yeah, it is t, which means here it is pi. Pi means 0. Yeah, and let us see an example. Understand the motion of a glider on a spring. Yeah, an air track glider oscillates horizontally on a spring at a frequency of 0.5 hertz. Suppose the glider is pulled to the right of its equilibrium position by 12 centimeter and then released. Where will the glider be 1 second after its release? What is its velocity at this point? Okay, so yeah, let's see. This is the starting point of the motion. Suppose the glider is pulled to the right, which means it's a horizontal, like a spring, and then there is a glider. It like pulls to the right, and here like 12 12 centimeter, and then really where will the glider be 1 point like 1 second after its release? What is its velocity at this point? Like here, you need to, if you want to know the time thing, you need to notice the frequency. Yeah, there is a relationship between frequency and the period. Do you remember that? Try to remember that. Like f equal 1 over t, which means t equal 1 over f. So then you can get the period. And after you get the period, you will know, oh, after like 1 seconds, where will the glider be? And the velocity, we can use the equation. So I think it's a little messed up here. Here, this is just the period. Okay, like yeah, like we know the f equal like 0.5 hertz, and the period is just 1/f equal 2 seconds. And the motion of the glider will be sinusoidal. It is released from the rest at 12 centimeters. So its amplitude is 12 centimeter. Yeah, and the 1 second is extremely half the period. You can see the period is 2 seconds, which means 1 second is half period, which means it will reach to the like a maximum, the lowest point, the lowest point, and then like from the equation, yeah, the lowest point like here it should be like 1, 2, it will be pi. So the velocity will be 0 using this equation. Actually, from this point, yeah, you also, we have already analyzed it. Here is velocity 0, and here is the maximum, and here is a 0, and here the velocity, here is the maximum, here is a 0, like that. Let me like access. Yeah, drawing a graphic was an important step that helps us to make sense of the motion. So like for to resolve those kind of questions, you try to draw like a graphic that will help you to resolve these kind of problems. Okay. I will actually those part like those equations is the most important thing in today's class, and you will know for the simple harmonics how to like calculate the displacement, how to like the move length, and how to calculate the velocity, how to calculate the acceleration, and yeah, these equations we will do a summarize at the end of this class, and like here connecting SHM like simple harmonics motion to uniform circular motion. Yeah, this is I just want to let you know how these two things be related with each other. Actually, this is not like the most important thing in this class, but you need to know that. Yeah. First, let us know like the circular motion and the simple harmonic motion are like are all motion that repeat. You can see if you like let a ball like runs in this circle, and there is a light from the projection, and here is the circle. It's turning. Its turn like, and then you will find that the ball will like from the sheet, the ball will like you can see here, and here is this one, here is this one, and here it will also like back, and if here it like from the sheet, it's just like a simple harmonic motion. Yeah, so that's like the relationship between the SHM and the uniform circular motion. Actually, the uniform circular motion can can be represented by like a simple harmonic motion. Like uniform circular motion project onto one dimension is simple like a harmonic motion. Yeah. Okay. Yeah, let's okay. Yeah, this one is A. Okay. The X component of the circle motion when the uh, particle is at H at angle. Let me try to make sure what is this one. It's a little weird thing. Okay, I don't know why these things. Uh, Okay, it is x, it is ang theta equal x equal a cosine theta. Yeah, okay. Okay, like uh, I will fix this up. I don't know why this point slides put it into the iPad. It will display very weird. Okay, the x like a component of the circular motion when the particle is at a angle like delta is theta is x equal a cosine theta. Like here, this is theta, and then the x component, which means this part, it is equal x cosine theta. Does it make sense to you? The angle at the latter time is theta equal omega t, which means it will run, and this angle will change, and the omega is the particle's angular velocity. Yeah, this is the how like how the the angular velocity. I think this kind of thing you have already learned in some mathematics thing or some college physics one. You can see this ball like runs in this circle, and the angular velocity, yeah, because the angular velocity means in this equal 2 pi over t, like yeah, yeah, like uh here. Yeah, and then the theta equal omega t, like equal 2 pi over t, which means as the time pass, how many angle the like particle move. Does it make sense to you? Okay, and therefore the particle's x component is expressed like x equal a cosine 2 pi ft. Yeah, because we just replace, yeah, because omega equal 2 pi f, am I right? So the theta equal 2 pi ft, and then x equal a cosine 2 pi ft. This is the same equation. You can see this is the same equation for the position of mass on a spring. Yeah, did you notice that? Yeah. So the x component of a particle in uniform circular motion is simple harmonic motion. Yeah, it is obvious because x component you project it to one dimension, and you will see the x component is just this equation, and this equation is just the simple harmonic motion. Okay, the x component of the velocity vector is equal this one. Sorry, it is so weird. There is just okay. Yeah, so because it is simple harmonics, we can use we can use we can use the equation we have already learned from the like a simple SHM, and Vx equal the the like a velocity now, and then just put it into different uh, here. I think yeah, from this thing. Oh, sorry, from this thing to this thing. Yeah, it divided to different direction x and y. The x component, the x velocity is just the v. Uh, sorry. Let me give you a more clear. Y. Okay. Oh, okay. So try to make it. Yeah, this is the velocity, the ball's velocity, and we will need to divide into x and y. And here, this is phi, am I right? Which means here, this is phi. This is phi. Because this and this is 90 degree and this is 90 degree, which means this is equal this one. So which means this is phi and this is sin. Sin like phi. Yeah, does it make sense to you? Yeah, you can use the circular function to represent it. And then the corresponding to simple harmonics, if we define the maximum speed to be this one. Yeah, this is we have already get from the simple harmonics. No, here. Yeah, here. Um, yeah. Mm, okay. I think it is here. So, uh, yeah, this is the maximum like velocity for the uniform circular motion. And then the x component of the acceleration vector is just yeah, the similar thing. So why it is just this weird? Okay, it's just the yeah, it's the similar thing. Yeah, since there is the acceleration, and then you divide it into x and y, and then use the circle functions and to represent it. This is like the x positions, like acceleration, and this is the maximum acceleration. And for simple harmonic motion, if you know the amplitude and the frequency, uh, sorry. Why it's just so weird? And the motion is completely specific. Yeah, you can see if you know the amplified. Yeah, you can use this and the frequency. You can use this equation to represent the acceleration. Also, you can represent the velocity and the displacement. Yeah, everything you can represent. So, sorry. Okay, I will adjust that. And okay, this is what I want to talk about the uniform circular motion. It's just a similar thing with like a simple harmonics motion. Yeah, you can use the equations for the similar equations to represent uniform circular motion. Okay, and let's summarize. And actually, this image is very important. Is the most important is the most important thing in this class. And you can find this in text book page 493. And yeah, the position, velocity, and the acceleration of objects undergoing simple harmonics motion are sinusoidal functions whose amplitudes and phases are related in a particular way. You can see we have already analyzed it. This is a position, and this is like the equation for the position. And do you know why the maximum is A? Because cosine is from -1 to 1. So when it is 1, it's the maximum. Okay, the same thing. The sin is from -1 to 1. So it is -1 is the maximum. Yeah, and this velocity and this acceleration is the same thing. Yeah, when the cosine is equal 1, it will the -1. It will the like maximum thing. Yeah, you can see it's the same thing when the cosine is equal 1, and then a maximum is 2 pi fa. Yeah, does it make sense to you? Yeah, any questions, just let me know. Okay, let me check some like SHM questions. The first one is a mass oscillates on a ha, ha, horizontal spring. Its velocity is Vx, and the spring exerts force Fx at the time indicated by the arrow. Yeah, you can see here. Which one is the right one? Yeah, like here in this position. What is the right one? Think about that. I think this one is yeah, in this, and the velocity because it's 1 is 0, and the fx is positive because it will go up, go up. Does it make sense to you? Yeah. Okay, a mass oscillation on horizontal spring, its velocity is Vx and the spring axis force Fx as the time indicated by the arrow, this time. And what's the velocity? Yeah, because it will go down. So, yeah, it will negative, and the net force, because it's equilibrium position, so the net force will be 0. Does it make sense to you? Yeah. Okay, let's see another question. A block oscillation oscillates on a vertical spring when the block is at the lowest point of the oscillation. Its acceleration AY is, when it is the lowest, the acceleration is what? Yeah, like yeah, the lowest point, which means the velocity is 0 and the acceleration, actually the acceleration, the direction is same with the net force direction. So it is positive because it's the lowest, it will go up. Yeah. So let's see the one exam. Mer like yeah. Okay. Measuring the swing of a tall building in a wind. Actually, the John Hancock Center in Chicago is 100 stories high. Strong winds can cause the building to swing, as is the case with all tall buildings. On particularly windy days, the top of the building oscillates with an amplitude of 40 centimeter, around like a 16-inch, and a period of 77 seconds. What are the maximum speed and acceleration of the top of the building? Okay. Yeah, we will use the relationship for amplitude, velocity, and acceleration from synthesis 41. Yeah, just this thing. Yeah, this one is very important because, yeah, actually all this class, out of this class talk about this part. Yeah, just remember these things. Okay, let's talk about this. Sorry. These questions, and actually, yeah, here the top of the building oscillation with an amplitude. We know the amplitude A and a period, and then what we can know? Yeah, we know the frequency O1 over T. It is around this one. And then we can use the equations for maximum velocity and acceleration to complete the sorry. So here, this is just the why it's just this. Okay. Yeah. Yeah, you can see we can use these equations to, after we get the frequency, we can easily to, and the amplitude, we can easily to get the velocity, maximum velocity, and maximum acceleration. In terms of the free fall acceleration, the maximum acceleration is like a point, like 0.27. Yeah, that's access. The acceleration is quite small. Yeah, you can see it is quite small. Like yeah, this is here. In terms of free fall acceleration, the maximum acceleration is yeah, the acceleration is quite small, as you would expect. If it is a large building, building like a occupants will certainly complete. Yeah, you can see the building will swing left to right. It will like a very dangerous. Even if you don't notice the motion directly, office workers on high floors of a tall building may experience a burden of nonsense when the oscillations are big, because acceleration affects the equilibrium organs in the inner ear, because this this simple harmonics will affect people's ear. Yeah, we will talk about tomorrow. And okay, let me talk about one thing. You can see the earthquake, yeah, has some like a big danger. It is very dangerous. So you know, like the earthquake has two different kind of earthquake. One is like a swing left and right, and the other swing up and down. Do you know which one is more dangerous for us, like for our building? Do you know? According this question, do you know that? Yeah, and I will tell you the answer, like the left, right, like a shake earthquake is more dangerous, because you can see the tall building, like because of the wind, like it oscillate in a very small like angle, yeah, every day. And when the like earthquake, like left and right oscillate at the same time, if there will be a situation we call it restless. Do you remember I mentioned it in the beginning of this class? And when this situation happened, and it will cause a very terrible like situation for the building. Yeah, we will talk about more. We will talk more about this situation like next class. Yeah. Okay. Okay. There is a very interesting like thing. Try it yourself, like SHM in your microwave. The next time you are warming a cup of water in a microwave, try this. As the turntable rotates, moving the cup in a circle, stand in front of the oven with your eyes level with the cup and watch it. Pay attention to the side to side motion. You will see something like a turntable demonstration. The cup is apparent motion is a horizontal component of the turntable's circular motion, like simple harmonic motion. You can observe it. Yeah. When you like hit the milk, just try it yourself. Okay, this is today's class. Yeah, so many things, like too much for you. Am I right? But don't worry. What you need to know is just remember these things, these part of things. Yeah, how to calculate the position, velocity, and acceleration of objects undergoing simple harmonic motion. And then in these equations, you will need to know the frequency, and the period is similar. It can be transferred with each other. So if you met the similar problem, and then you just use this equation and try to find the period, try to find the frequency, use this equation to resolve this problem. And like I talked in these questions, yeah, try to like draw the graphic when you can, and that will give you a clear like understand for these questions. Yeah, this is what we talk about in this class. Too many things, but just remember these things. Okay. Okay, let's finish today's class. Thank you for listening, and I hope you can understand what I'm talking about. And if you don't, yeah, that's totally fine. Please let me know, and let's try to figure out together. Okay. Okay, see you. Bye. Okay, let me